students, I'm going to be going over the properties of water in this short lecture video. It corresponds to the Chapter 3, Section 2 reading, which goes over the properties of water, goes over solutions, pH, and buffers. So let's go ahead and get started. The most important thing to remember when trying to understand the properties of water is that it all comes back down to water's polar nature. Okay, so if you just think of the word polar, it usually means opposing, and that same principle is going to apply here. Okay, and a polar molecule is basically a molecule that has both high electronegative elements and low electronegative elements. Okay, so if you want a refresher on electronegativity, please go back and watch the previous video where I covered basically the nature of atoms and bonds and how all of it is governed by electronegativity. So you can go over that concept there. Okay, now the chemical formula for water is H2O. And basically, it's made of one atom of oxygen and two atoms of hydrogen. So, in the periodic table, oxygen has 8 as the atomic number, so this stands for the number of electrons it has. And the first 2 electrons in 8 are going to go in the first shell. After they fill the first shell, in the second shell, the remaining 6 will enter, and there is just space for 2 more electrons that need to be filled. And they're going to be filled by hydrogen. And in the periodic table, hydrogen has 1 for the atomic number, so it has 1 electron. And because it only has 1 electron, it only needs to fill the first shell, so it needs space for 1 more. So basically, this molecule is a covalently bonded molecule, and it's going to share the electrons. So oxygen sharing 2 electrons from hydrogen, and hydrogen sharing 1 electron each from oxygen. However, not all covalent bonds are the same, especially when you have a very electronegative element and a very low electronegative element. So oxygen here has a high electronegativity. That means it really wants those last 2 electrons. Okay? So it really wants the 2 electrons. And on the other hand, hydrogen only has 1 electron, so it is pretty weak in its electronegativity versus oxygen, which is strong. So these bonds are known as polar covalent bonds. And in covalent bonds, the atoms are sharing the electrons. That means it pretty much spends like even time or distribution around the atoms, okay? However, in polar covalent bonds, they're kind of like the bond you might have with a younger sibling or somebody who is annoying in your life. So, if you've ever experienced having to give something to somebody, they said they just needed it, then they need to borrow it from you, but instead they've taken it and now it's theirs, but they never stole it, they just borrowed it. That's what a polar covalent bond is. Oxygen is borrowing the electron from hydrogen, but it's basically just keeping it. That's pretty much how a polar covalent bond is. So polar molecules, they're not quite like ionic molecules where basically there's a full-blown positive or negative charge. They're technically neutral, okay? And this doesn't have a formal negative charge, or this end doesn't have a formal positive charge, but they are a little bit charged. So in chemistry, we refer to that as a delta. So this is a delta negative, and this end is a delta positive. So it's slightly negative here and slightly positive on this end. Okay? So let's continue to the next one, which is the consequence of polar molecules. So polar molecules then are going to form hydrogen bonds. And if you recall from yesterday when we talked about hydrogen bonds, okay, these are very weak bonds, all right? And they form between different molecules. So they're not inside of a molecule, they're between multiple molecules, so that adds to their weakness. However, they are strong in large numbers, and it's pretty amazing what they can do in large numbers. Okay, so if we look here, this delta positive end of the hydrogen is somewhat attracted to this delta negative end of the oxygen, and we see that happening all over. So you can have about 3 to 4 hydrogen bonds form per water molecule. And you can see how water is kind of oriented itself, that this oxygen is oriented towards the hydrogen here, and these are very weak bonds. So if you recall from yesterday's video, I called hydrogen bonds, I tried to give the analogy of it as friendship, okay? Because it's not quite the same as completely sharing an electron or resources like a committed relationship might be. It's not quite at that level, and usually you're going to have more than one, friend, hopefully. All right? And because of that, it is strong in numbers. All right? So that's a way to kind of remember it. The hydrogen bond on its own is pretty weak, but it's strong in numbers, and you'll see hydrogen bonds play a huge role in molecules again and again and again. So look for those kind of patterns. Okay, the other cool thing about polar molecules is they actually attract ions. So this is why water is what we call a universal solvent. So because of the polar nature water has, it is considered the universal solvent. All right, so you can see that sodium chloride is table salt, and in this case the water molecules, all the positive, the delta positive ends are oriented towards this because it has a negative charge. On the other hand, all the negative oxygen ends are attracted to the sodium ion because it has a positive charge. So again, opposites attract, and we can see this with polar molecules. That's why they're really good at breaking apart different compounds, because they have both the positive and negative end, and their forces, because there's so many of them, will overpower whatever was within the molecule itself. Now let's talk a little bit about nonpolar molecules, because they do play a role in biology. Nonpolar molecules are pretty good at protecting things, and we'll see that more come into play with cells. So how do they form? Well, basically they're with elements that have little to no difference in electronegativity. So anything that's like a low electronegativity, or anything that's like medium to high to low. Okay, so there's very little difference. Usually it's not going to be anything that's highly electronegative. And you can see this a lot with compounds that have carbon and hydrogen. Okay, they typically tend to be nonpolar, and that's because they have a more even electron dispersion. So methane's a really good example of a nonpolar molecule because there's very little difference in the electronegativity. So the rule usually is, like, if they're closer together on the periodic table, they're going to be more nonpolar. The further apart they are, the more polar they are. Okay, so one thing I would suggest that you do is you take notes on this really great video that's linked in the Google Slides on the properties of water. So it's a TED Ed video. It's 4 to 5 minutes long, and it does a really good job. So in case you want another take on this topic, you have a good option as well. So let's go over the specific properties of water. And remember, one thing to always keep in mind is everything comes back down to hydrogen bonding and water being a polar molecule. Okay, so this is like one of those big topics in biology you see over and over again. Now let's talk about the first property, which is a high specific heat. So water requires a lot of energy to change phase from liquid to gas. And that's because when the energy first comes in, it has to break all of these hydrogen bonds. So it might be able to break one bond, but you're going to need a lot of energy to break all of these bonds in order to create your water vapor. Okay, and this is going to come into play later on when we think about how organisms cool themselves down. The next property we're going to talk about is surface tension. So you may have heard of some animals that are able to walk on water, like water striders, or the basilisk lizard. It's also sometimes called the Jesus Christ lizard because of the legend. All right. But surface tension is due to a high amount of hydrogen bonding. So this phenomenon occurs where at the surface of any like liquid and air, you're going to have more hydrogen bonding occur. So you can see that over here that you have just more water molecules, and they're more closely bonded together than further out. And what this does is it creates the surface that's more resistant to change. So animals can kind of walk on it, they can, you know, manipulate it. It's really difficult to break the hydrogen bonding on the surface. The next property we're going to talk about is adhesion. So it's hard to think about it like this, but lots of substances have like pockets of positive and negative charges, and water molecules are able to create their hydrogen bonds to adhere to a surface. So typically, this is why, in many cases, when you're pouring water into a cylinder, that there's a little bit of a curve water makes because it's adhering to the surface. So if you've ever had to like measure something in a graduated cylinder, you'll realize water curves and you have to read at the bottom of the curve. So that's adhesion. Next, I'm going to talk about cohesion, which is pretty much just hydrogen bonding between water molecules. So again, when we talked about that delta minus and that delta positive, so the minus, the negative and positive charges, the orientations of the hydrogen and the oxygen, it's just that water is able to hydrogen bond really well with other water molecules. And this is what makes water sticky in a sense. Okay? So if you're ever looking at why water droplets run together, it's probably because of cohesion. The last thing we're going to talk about is capillary action, which is this awesome property that allows water in some ways to climb. So I remember one of the instructors in Lowell, when I started teaching there, he was talking about how he approached teaching capillary action by having a bucket of water in one end of the classroom and like a rope that connected that bucket in one end to an empty bucket on the other side. So what would happen is then the water would climb up the rope and then deposit itself on the other side. And that's like a really, really kind of big example of this, but water is able to use capillary action in some ways to defy gravity, so it's a little cooler than us. Um, and capillary action is just a combination of adhesion and cohesion, so it's able to bond onto something, and then it's able to hydrogen bond to other water molecules and, in a sense, pull those molecules up a vessel. And this is how usually plants are going to be able to transport huge amounts of water up very tall trees. Okay, and that's pretty much it. Thank you guys.